Welcome to the course on social network analysis again, and this is the third chapter on network growth models. So in the previous chapter, we have seen how to quantify a network. We have seen different metrics that we can use to quantify a node or an edge or a graph, right? We have seen three levels of quantification: microscopic, macroscopic, and mesoscopic. Level of quantifying nodes, edges, and networks. And we have also seen properties like degree distribution, right, scale P properties, and so on and so forth. So when we analyze networks, right, so the first important thing is to scrape data from some social network, right. Now what happens is that when we try scraping data, there are multiple problems. So first problem is, say, there are limitations in the crawling process, right. Crawling sometimes takes a lot of time. Crawling also has its limitations. For example, you may not be able to crawl those nodes or those edges which are private, for example, right, protected in some ways. At the same time, the current networks, social networks like Facebook, Twitter, it's so huge, right, and you may not be able to scrape the entire social network as a whole, right. You may scrape a partial network, for example 1% or whatever 0.5% of the network, right. So and oftentimes, since we do not know the exact connections, right, so sometimes we end up having connections which are partial, which may not be complete. Therefore, most of the analysis that we do on the partial network may not be significant enough, right. So what people generally do in that case, in social network analysis, people generally create graphs synthetically, right. It's kind of a synthetic network lab. I mean the network that you generate in your lab, and then you test all your models on the synthetic network, right. But we also need to remember that the synthetic network or the toy network that we develop or that we generate should have properties that the real world networks exhibit, right. It should not be the case that your synthetic network looks completely different from the real world network. Otherwise, there is no point in testing your method on a network. So what's the idea? The idea is that, say you have a synthetic network, you test all your models. It can be, say, community detection model, it can be link prediction model, or whatever, anomaly detection problem, right, model, and you run those models on the synthetic network and see how these models perform, right. You can also compare across models on different synthetic networks, and then since you have control on the generation of the synthetic network, what you can do, you can, say, increase the size of the network, you can increase the number of nodes, number of edges, decrease, and so on, and then we test the scalability of your models on different different networks or different sizes, right. So you can do a whole bunch of stuff because now you have control on the network generation process. So you can create large network, small network, whatever, right, partial network, and so on. And then when we do that, and when we compare models on this synthetic networks, then we choose the best model, for example, and then then you say that, okay, look, this is the best model for link prediction, and you use this model for production, right. So you give this model to somebody who is doing link prediction task, and he can readily use this model for the production. Okay. So we have a lot of flexibility in terms of the size, right, or different variations of a network, which we may not have when you scrape a data set. For example, when you scrape a data set, how do you know that, I mean, how do you sync the network? When you sync the network, when we reduce the size of the network, you need to remove some nodes. How do we remove nodes? You can't remove nodes randomly, because when you start removing nodes randomly, the network may look, the network may start exhibiting different properties that the original network may not have, right. So there should be a systematic way to control the network, and synthetic network is one way of systematically controlling the generation process. So, so there are basically two reasons. The first reason is that we may not be able to deal with such a gigantic real world network, therefore we can generate synthetic networks and test our models on the synthetic networks. This is number one. Number two is that since we have control on the entire network generation process, we can change the process accordingly, and then we can create small network, big network, or semi large network and so on. Okay. So, and all these models that we generally develop, right, they in the initial stage they may not be that scalable, right. So, when we test this non-scalable models on the massive networks, a massive real world network, right, it would take huge amount of time, for example, right. So, if these models take huge amount of time, then how do you compare across different models, right, that would take ages. Okay. Therefore, we use synthetic networks and then test the efficacy of these models on synthetic networks, and then we finalize a particular model and then send it for production. Okay. So, synthetic networks generated using theoretical network models, this is very important. So, we will discuss in this particular chapter a series of network models, network generation models that we use for synthetic network generation, right. Again, I am repeating, it is very important to remember that the synthetic networks should exhibit real world properties. It should not look like a random network, right, because otherwise there is no point in generating a real world like synthetic network. Okay. So, this underlying mathematical foundations is very important. So, when we draw a synthetic network, we need to understand how real world networks are generated. If we come up with a mathematical model to understand how a real world network is generated, right, we can use the same mathematical model to create a synthetic network, right. For example, if we know that when a node comes in into the system, it is going to join, it is going to be connected with a node of highest degree, for example, right. If we know that okay, this process is followed when a real world network grows, right, we can actually mimic the same process to create a synthetic network. Okay. But what is the exact underlying mathematical process which which is generally followed for the network growth process? Okay. So, the mathematical modeling is very vital, and it can actually differ across different models, right. So, we will discuss random network model, we will discuss preferential attachment model and so on and so forth. And basically over time people tried to come up with sophisticated models to mimic a real world network. Now, what do I mean by a real world network, mimicking a real world network? It means that in the synthetic network, the properties, for example, the clustering coefficient, degree distribution, right, path length, right, diameter, all these network properties that are generally observed in a real world network, those properties should also be preserved in a synthetic network. Okay. That is very important. So, over the years people tried coming up with different different growth models to mimic how a real world network grows over time, and they actually test the efficacy of their growth models by checking whether a particular property of a network is actually preserved, right, or remains same across synthetic network and real world network. For example, you generate a network and then you test the degree distribution of the network. If it follows a power law, then you say that okay, it looks like a real world network because real world network also has power law degree distribution. Okay. So, power law is one property. There are many such properties, and all these network growth models basically try to satisfy at least a subset of these properties that a real world network exhibits. Okay. So, we will see over this particular chapter that how the field of network growth models evolved over time and how more sophisticated models came into the picture, and they actually tried to mimic real world properties. Okay. So when we say that the synthetic network essentially mimics real world properties, now what are the real world properties that we generally look at? We generally look at these three types, right? So basically people studied a lot of such real networks, and then they realized that all these real networks, they basically exhibit a high average local clustering coefficient. So local clustering coefficient is something that we discussed in the last lecture. If you remember, it basically says that for a given node you look at their neighbors, so and then you create an induced subgraph of neighbors, and then you look at the actual number of edges among the neighbors, and you divide it by the possible number of edges among the neighbors. That is the local clustering coefficient, and then you basically take an average across all the nodes, right? And it turned out that for real world networks, surprisingly, the average local clustering coefficient is pretty high, okay, meaning that even if say a node has very high degree, for example degree 100 or degree 200, right? So as the number of as that degree increases, the denominator of the clustering coefficient will also increase. The denominator basically says that what's the total number of possible number of edges that can be formed across neighbors. This is NC2, so D is C2, D is the degree, right? So even if the degree increases, right, clustering coefficient remains almost same, right? And with a massive network, it was shown that on a network of say 1 million nodes, right, the clustering coefficient is still around 0.12, 0.13. 0.12, 0.13 is actually a pretty good number, right, when we look at the nodes with very high degree and so on. So this property should be preserved in the synthetic network. Okay. The second property that was observed across real world networks is the small world property. Okay. I will discuss what is small world property, but if you remember in the last lecture we briefly discussed what is small world property. Basically says that if you take any pair of nodes from a network, the distance is very small. The shortest path distance between any pair of nodes in a network is very small, and how small it is we will discuss today. So small world property, and then we have this scale free property. So scale free property is again basically the degree distribution should follow a power law, right, and power law itself is scale free. So when you plot the degree distribution of a synthetic network, it should follow a power law, okay, and the kind of power law that we are expecting, right, is basically k to the power minus gamma, where gamma ranges between 2 to 3, right. So if your synthetic network follows this kind of property where gamma ranges between say if not 2 to 3 but at least 1 to 4 for example, then you say that okay it has a scale free property. So we'll try to see which network growth model actually follows all of these three properties. Okay. So high average local clustering coefficient we discussed. It turned out that massive Facebook network with users having average 100 friends, the clustering coefficient is still 0.14, which is pretty large. Okay. In fact, a graph with 150 million nodes, the expected number of the local clustering coefficient is unexpectedly very high. So which may not look like a trivial observation, because we basically we can assume that as the network size grows, the average clustering coefficient may decrease, right, naturally. But yeah, it actually decreases, but it's not like it decreases massively. It's not like I mean the clustering coefficient distribution doesn't follow the power law property. Okay. So small world property, let's discuss about the small world phenomena, right. So the name suggests the world is small. Okay. So what does it mean? It basically means that if you want to send a letter, okay, to the president of US, right, the distance that this letter will traverse, right, the distance is pretty small, right, and how small it is. So, it turned out there was a very interesting social social science experiment way back 1967, 1968 by Stanley Milgram, right, and it turned out that the shortest path distance between any pair of nodes in a network is 6. Okay. So, I mean it sounds very unrealistic, right. So, it basically says that if we think of this world, right, as a social network, think of this user-user interaction network, right, or a person-person interaction network, right, in the entire world, if you choose any pair of users, any pair of individuals, the distance is less than equals to 6. Okay. It sounds little unrealistic, but I will show you that it is not that unrealistic if we do it mathematically, if we try to calculate these things mathematically. Okay. But let us try to understand this experiment done by Stanley Milgram, right, in 1967, and this experiment is called small world experiment. So, what what he had done, he basically chose two extreme cities, I mean 2 cities which are far apart from each other in USA. One is Nebraska, right, Kansas and Nebraska, and other is Boston. Okay, Nebraska is here and Boston is here. Okay, two parts of 2 different regions of United States, right, and then he chose some individuals here, right. So, this is your source, Nebraska, and Boston is your destination. Okay. And then you choose some users, some individuals here, okay. And then to each individual you give a letter, okay. And in the letter it is mentioned that the destination is in Boston, right. So, the task of that individual is to send that letter to the destination. The destination is in Boston, an address in Boston, right. And how the individual can send this letter? Individual can send this, I mean if the individual knows the destination address directly, so he can just go and drop the letter to the destination. Okay. If the individual does not know the destination properly, what he can do, he can basically choose a friend who the individual thinks may know the destination better. Okay. Say this individual is X, okay, and so X, if X does not know the destination, so X will choose another friend. So, Y should be the friend of X, right. So, X will choose one of his friends Y, which X thinks that the friend Y knows the destination better than X. Okay. So, if I do not know the destination, I will basically pass the letter to somebody who I feel that knows the destination better. Okay. So, when the letter comes to Y, Y will again see the destination address, and if Y knows the destination, Y will directly send it. Otherwise, Y will again choose one of his friends who Y assumes that knows the destination address better. Okay. So, this is the process. So, therefore, you see that when the letter passes and when you pass a letter from when a letter is passed from X to Y, right, X will write X will basically write his address and pass it to Y, and then again when Y passes it to Z, so Y will write his address and pass it to Z. Okay, this is the strategy. Okay, and then around 296 such letters were given to individuals in Nebraska and Kansas, and it turned out that and say when the letter moves from X to Y, then Y to Z, you can easily see the number of hops, and you keep on counting the number of hops for letters, right. Now, it turned out that there was at least one person, one individual who knew the destination address directly, and he directly sent the letter to the destination. Therefore, the minimum hop that was required to send the letter was 1, and the maximum hop that was required right, to send the letter to the destination is 11. Okay. Of course, I mean out of 296 only 64 letter reached the destination, right, and in out of these 64 cases the minimum was 1, the maximum was 11 and the median was 5.2. Okay. So, and from this number 5.2 Milgram coined the term 6 degree of separation. 6 degree of separation, it is a very famous term, 6 degrees of separation, meaning that if you choose any two individuals, right, from this world, right, there would be actually 6 hops between these two individuals. Okay. So, average path length, average shortest path length between any pair of nodes in a network is 6. Now, why 5.2 is approximated to 6, why not 5, I do not know. There is no reason. I mean Milgram thought that okay, I mean we should always take the upper limit, not the lower limit, therefore he suggested this 6 as the shortest path distance, right. I mean Milgram was very famous for all these very surprising interesting experiments. Of course, he was a social scientist, so this was one of the experiments that for which he was very famous. And of course, people then started shouting because this number is very insignificant, only 64 letters were actually sent, 64 letters reached the destination. How can you come up with such a strong claim based on only 64 letters, right, 64 samples, right. But nevertheless, I mean later on people actually tried to come up with even better measures and so on. For example, there was an experiment done by Leskovic and his team in 2007, and the same experiment, the small world experiment, was performed on Microsoft Messenger. So right, Microsoft also had its own messenger kind of service like we have Facebook Messenger these days, and the same kind of experiments were actually conducted, and it turned out that actually the number is 6.6, which is quite same as the one that Milgram suggested with only a tiny amount of samples. The same experiment was again repeated in 2011, right, but this time on the Facebook network, because Facebook that time became already popular, and this experiment, the repetition happened 2 times. In 2011 it was happened, and it turned out that the average distance is actually 4.74 in the on the Facebook network, right. In 2012 the same experiment was repeated, and the average distance turned out to be 3.74. So as you see, over the time, as the size of the network increases, right, it is also obvious that the distance between individuals should also decrease, and it is actually happening from 6.6 to 4.74 to 3.74 and so on, right. So in fact you can also do the similar experiment on the Facebook graph, on the Facebook social media. There is an app, there is a very interesting app, and through that app you can check what is the degree of separation, right, of your user account from the other users present on Facebook. Actually I did this experiment, I tested it to check my degree of separation. It turned out around turned out to be 3.74, 3.75. You can also check your degree of separation, right. So this small world phenomena is basically very famous, and it basically says that the average path length of any pair of nodes in the network is it should be proportional to the log of the size of the network. Okay. So average path length is denoted by this one, mod of L. It is proportional to the log of n, where n is the number of nodes in the network. Okay. So if you prove that your synthetic network follows this kind of property, right, therefore you can basically say that okay, I mean one property is now ticked, right. So at least with respect to one property of real world network, your synthetic network behaves quite similarly. Okay. So that was small world property. The third property is scale free property, we have already discussed earlier. So scale free property basically says the degree distribution should follow power law, right. It means that so if k is a degree, so this pk, right, it is also denoted by this one, it should be k to the power minus whatever gamma or lambda, or gamma ranges between 2 to 3 or 2 to 4, right. So if you prove that your synthetic network actually follows this kind of power law degree distribution, you can say that it resembles with the scale free property that the real world network exhibits. Okay. So we stop here. In the next lecture we will discuss the simplest network growth model called random network growth model. Okay, that is the simplest one, and although it is a very simple method, but we will see that it basically follows some of the real world properties that we have been talking about. Okay, thank you.